We can also see how the carbocation rearrange in these type of reactions. Because the reaction of a secondary alcohol with a hydrogen halide is an SN1 reaction that forms a carbocation intermediate. Always check for the possibility of carbocation rearrangement. So let's see here, we have a secondary carbon carrying a hydroxyl group, and you add hydrogen bromide. First thing happen is OH group protonate with the hydrogen of HBr. So now we have a protonated alcohol. Okay, protonated alcohol, we have made it as a good leaving group. So it can just fall off, right? Once it fall off, you have a positive charge right there, and that's a secondary carbocation. Now, we have seen before in Chem 1, a carbocation can rearrange to the more stable carbocation. So this is a secondary carbocation. A hydrogen can shift. We call it as 1,2 hydride shift. 1,2 hydride shift. So there is a hydrogen on the neighboring carbon, and that hydrogen, this hydrogen right here, gonna shift to this carbon and creating a tertiary carbocation. You see here? Now this is much more stable carbocation. Now there are two instances. We have a secondary carbocation, we have tertiary carbocation. If the bromide adds on to the secondary carbocation, we're going to get 2-bromo-3-methyl-butane. If the bromide attacks the tertiary carbocation, we get 2-bromo-2-methyl-butane. So that is the major product compared to the secondary carbocation product. Okay, so there is a rearrangement of the carbocation making a tertiary carbocation by way of 1,2 hydride shift, and that was the main product. Why is it important to be able to convert alcohols into alkyl halides? So far we learned that we had alcohols and we converted them to alkyl halides. But why do we do that? Because alcohols are readily available, but they are unreactive. Okay? Whereas alkyl halides, they are less available, but they are very reactive and can be used to synthesize a wide variety of compounds. Alkyl halides, we can use them to make natural products, or maybe a part of a natural product, because they are very reactive. So alcohol is here, you can use alkyl halide, and then you can heat it with hydrogen halide and form alkyl halide. And once the alkyl halide is been formed, it can undergo many reactions. With a methoxide, it can form an ether. With an alkyne group like this, acetylide group like this, can form a carbon compound containing a triple bond, and this can undergo further reactions depending on the target molecule we want. And then also these alkyl halides can react with cyano groups, cyanides, forming alkyl cyanides. And this alkyl cyanide, we can add a water molecule, we can cleave it, we can make amines, we can make carboxylic acids, we can make amino alcohols. A lot of other products you can form with this intermediate also. Okay. Other methods to convert alcohols into alkyl halides. So here's another one. So far we learned about alcohols reacting with hydrogen halides. Now another method is reacting with phosphorus tribromide in the presence of pyridine. Pyridine is a solvent and can form ethyl bromide. Similarly, this is PBr3, this is PCl3. Phosphorus trichloride will convert it to alkyl chloride. And then in the presence of pyridine and thionyl chloride, SOCl2 is thionyl chloride, can convert to alkyl chloride again. Okay. phosphorus tribromide, phosphorus trichloride, and thionyl chloride. So these are the names of these compounds. And these are some other methods where we can convert alcohols to alkyl halides. Commonly used methods for converting alcohols into alkyl halides. Alcohols heating with hydrogen bromide forms alkyl bromide. Alcohol heating with hydrogen iodide can form alkyl iodide. With zinc chloride form alkyl chloride. With PBr3, PCl3, SOCl2 forms alkyl bromide, alkyl chloride, and alkyl chloride, another one. Okay, so these are some of the methods, commonly used methods to convert alcohols into alkyl halides. Primary and secondary alcohols can be activated by being converted into sulfonate esters. Remember, we learned earlier that we can activate alcohol by adding an acid and making a good leaving group O oxygen with 2 hydrogens. So the alcohol can leave as a water molecule. And similar to that, another method that we use to activate alcohol group to make it a good leaving group is by reacting with a sulfonyl chloride. So this is sulfonyl chloride, and we use pyridine as a solvent. So when you do this reaction, this oxygen is going to combine with the sulfur center and form a bond and form a sulfonate ester, leaving chloride. A sulfonate ester is formed when an alcohol reacts with sulfonyl chloride, and it makes a good leaving group. And these are some common sulfonyl chlorides. Paratoluene sulfonyl chloride, we also call it as TSCl, or tosyl chloride or tosylate. And then another one, methane sulfonyl chloride, trifluoromethane sulfonyl chloride. So these are common sulfonyl chlorides. So these sulfonate esters that forms can react with a nucleophile. So this is the one that we have seen earlier. Now sulfonate ester react with a nucleophile. Excuse me. Now if you identify this part is coming from an alcohol, and we have activated this alcohol by adding a sulfonate ester. Now this is a good leaving group, that is in yellow color, that's a good leaving group. So if you have a good nucleophile, methyl sulfide nucleophile can attack the primary carbon here and leave this whole group. By making OH a good leaving group, a sulfonate ester, the reaction will take place very smoothly. Okay, so we have activated the alcohol. So the new compound formed is this alkene group, butyl group with sulfur and a methyl group. So we have made this new compound with the sulfur. Okay, and not only methyl sulfide, you can use any other nucleophile to make a new compound you want. Now this is a cyano group, cyanide group. Cyanide carbon attack this methylene carbon here and leave this whole group and making a good leaving group. So this is the product that we obtained. Now the alcohol, originally we had the alcohol converted to cyanide group. Now we can do, if you want, any other reactions on this one. Okay. Sulfonate ester has an excellent leaving group that we have seen in the previous slide. So this is the sulfonate ester. You see here, once the hydrogen left, so the resulting sulfonate ester is resonance stabilized. You can see, if you remember the resonance structures from your general chemistry 1, it's a electron delocalization. So the negative charge on this oxygen with 6 electrons on oxygen. One of the lone pairs can form a bond here, and then it can have resonance with the other 2 oxygens like that. Its resonance stabilized, making it a very good leaving group. Configuration of the product depend on how the alcohol is activated. Excuse me. Now here we have an alcohol, and with the configuration, you see here H is coming towards you, hydroxyl group is going away from you, and methyl group and the alkyl group, you can consider them as the same plane as the as this board. And then OH is away from you, hydrogen is coming towards you. And we are doing an experiment with phosphorus tribromide pyridine and a methoxide ion. And then the resulting product is a methoxide attached to carbon. Okay, and so we have the alcohol configuration right here, oxygen, and this also has the same configuration as the final product. And if you look at the second one, we have the same starting material as before. Now this one you are making a tosylate sulfonate ester with pyridine, making hydroxyl group a good leaving group, and then you have your nucleophile methoxide. Now the product here configuration is opposite that of the alcohol. Normally these reactions are SN2, and if you remember SN1 and SN2 reactions, SN2 reaction we get inversion of the configuration, inverted configuration, whereas if it is SN2 we get inverted configuration. SN1 it's a 50-50 mixture because you have a carbocation formation, right? Now this reaction also, the very first one is also SN2 reaction, second one is also SN2 reaction, but here same configuration as the alcohol as your product, but the second one configuration is opposite of that of the alcohol. Now let's see what's happening here. 2 SN2 reactions or 1 SN2 reaction. Now this is the reactant. Phosphorus tribromide and pyridine. Alcohol group is going to activate it with the PBr2. Now if the activation takes place, it's just the PBr3 adding on to the oxygen, so it retains the configuration. Once it's been activated, bromide is going to do the backside attack of carbon because it's an SN2 reaction, and then this group leaves. So then you will see inverted configuration. Bromide is on the opposite side than the alcohol. That's what we should expect for SN2 reaction. But it doesn't stop here. We have another nucleophile methoxide. Now this also going to react with this carbon in SN2 fashion. So it's again a backside attack coming from this side, and bromide leaves, making it again inverted configuration. Since there are 2 SN2 reactions, it will retain the same configuration as the alcohol to begin with. Okay, and in the second one, we started with the same starting material. You have a tosylate making a sulfonate ester, making the sulfonate ester only hydrogen leaves, and then the tosylate going to be on oxygen, attached to oxygen. Now you have the methoxide. There are no 2 SN2 attacks, it's just only one. So in that case, since the methoxide attack from the backside and then tosylate leaves, so it has an inverted configuration. Okay, so that's what's happening over here. I'll stop this section over here, and we will start the acid catalyzed dehydration of an alcohol in the next section.